to welcome you to the 6th International Congress on behalf the International Congress on Information and Communication Technology through Zoom on behalf of ICICT 2021 and Global Knowledge Research Foundation. As we are passing through an unforeseen circumstances due to COVID-19, we do wish everyone and their families a safe time, and we hope that we'll pass through this together. Further, with immense happiness, I would like to share that we have received an overwhelming response this year from across 90 countries, where 1,150 papers were submitted and 350 were accepted, contributing to the success of this conference. And the papers will be published in 4 volumes this year. We're very thankful for our guests' presence on this platform and to join us digitally this year through these unprecedented times. And hopefully these conferences will still be fruitful in terms of technical knowledge, and we hope to enjoy the last few sessions of this amazing 6th International Congress. I'd like to take a brief moment quickly just to thank our chair, Dr. Paweł Dymora from Poland, who is our respected session chair, just to say thank you and to provide a little bit more context about Dr. Dymora. So Dr. Dymora was working as an assistant professor at the Department of Complex Systems Faculty of Engineering and Computer Engineering in Rzeszów University of Technology. He is also
Rzeszów University of Technology, yes.
I do apologize.
No problem.
In this session, not just to you, Dr. Dymora, to any individuals, if I do mispronounce your names, there was no intention to do that, so I do apologize. But Dr. Dymora has also has main interests in areas including data mining, process discovery, complex systems, anomaly detection, BPMN databases, computers, and sensor networks. So I'm sure he'll enjoy your presentations today. Doctor, if you wanted to say anything just before we started, and then we'll start with our first presenter.
I would like to welcome everybody at this today's session. I think that today's session will be a good experience, scientific experience, especially for all of us, and best wishes for all.
Thank you, Doctor. We'll move on to our first speaker now, who is Suleiman Ali-Jabal from Saudi Arabia, whose paper title is An Integration of UT-AUT and Task Technology Fit Frameworks for Assessing the Acceptance of Clinical Decision-Supported Systems in the Context of a Developing Country. So welcome, Suleiman. If you are here, sir, if you could unmute yourself, and we can carry on and start your presentation. Sir, if you can hear me, feel free to unmute yourself.
Hello.
Hello.
Can you hear me?
Yes, we can hear you now, sir. I'll just stop sharing my presentation and allow you to connect your presentation and continue.
Yes. 1 second. Do you see my presentation now?
Not currently, sir.
Sorry about that. 1 second. We'll try again. It's not working.
But just in this time, while Mr. Suleiman gets his presentation sorted, I would just like to remind presenters that we are limited in time today. We do have one more session to go. So if you could please limit your presentations to 12 minutes, followed by a 3-minute Q&A. If I do interrupt, I will try and do it as you're changing slides, just to remind you to try and conclude within the next minute or so. So thank you for that cooperation. Mr. Suleiman, if you are ready with your presentation.
Is it clear now?
Yes, we are able to see and hear you. You can carry on, sir.
Yeah, thank you so much. Hello, everybody. My name is Suleiman Ali-Jabal, a PhD student at Newcastle University in New South Wales in Australia. It is a great opportunity to participate and present my paper in this conference. Me and Prof. Shah have prepared this paper with the title and integration of UTAT and task technology fit framework for assisting the acceptance of clinical decision support system in the context of the developing country. I hope by the end of my presentation, you will have a better understanding. This is the outline of my presentation today. I'm gonna start with the introduction about clinical decision support system, then talking about the aim and the objective of the study. After that, the significance of the study, then there is a research methodologies, then the data analysis, after that, the result and conclusion. So in the beginning, what is the clinical decision support system or CDSS? CDSS are computerized tools developed to help healthcare provider make a quality decision regarding patient treatment and improving clinical management. In other words, CDSS is application or system that help health professionals such as surgeons, nurses, general practitioners to provide relevant information which can help them to make a decision as well as to improve patient care. In addition, CDSS can provide some recommendation and suggestion for the user. There are many benefits of using CDSS in healthcare sector. Many studies have shown that using CDSS will help a lot to reduce medication errors. Several studies have shown that the use of CDSS could provide better healthcare services and support doctor to make a decision and reduce medical errors. This will help a lot to improve the healthcare services, especially in developing countries. Early treatment by using CDSS contributes significantly to improve the cost effectiveness. Using CDSS help to reduce diagnosis and investigation of the patient. Using CDSS has improved the patient treatment quality, and this leads to increased well-being among the patient. The aim and the objective of this study to discover and identify the factors that influence the acceptance of CDSS in the developing countries. The following support goals are to investigate further advantages of using CDSS, also to extend the current knowledge regarding using CDSS in health care. The significance of the study, the literature review indicated that there has been a very limited study on the use of CDSS in developing countries. So this leads to the need for in-depth research in the area of acceptance CDSS in developing countries. Solomon 2016 stated that it is necessary to investigate both positive and negative aspects of using CDSS in developing countries to generate more knowledge and recommendation about the issue. This study helped to understand the need or requirements of the general practitioner regarding CDSS. The technology acceptance. Study the technology acceptance is very important in order to identify and discover the factors that influence to help to have a successful adoption of and implementation of the CDSS. Understanding and the attitude of individuals to use specific technologies is help to design appropriate software to the users. In this study, we integrated the TTF model with the UTAT model to be the main assessment framework for this study. In the beginning, I'm gonna start with about the unified theory of acceptance and use technology, which is UTAT, called UTAT model, which has been developed by Finkitash and other 2003. The UTAT model, as you see in the figure, contain 4 principal factors, which are performance expectancy and social influence and facilitating condition. It also include 4 variables, which are gender, age, experience and volunteers reviews. As you see, the three factors, which are social influence and performance expectancy and over expectancy, have immediately affect the user behavior intention. However, the facilitating condition have immediately affect on the user behavior. Actually, UTATE model has been developed by as a result of the investigation 8 different acceptance theory and models, and take account of the most significant factors that influence the technology acceptance. The second model, the task technology fit, has been developed by Goodhue and Thompson 1995. Task technology fit defines as the degree to which technology helps the user in performing their task. In other words, TTF means the degree of alignment between the capabilities of the technology and the requirements of the task that should be performed. TTF model indicates that technology will have a positive influence on the performance when the abilities is fit to the task requirements. As you see, there are two main factors in the TTF model, which are task characteristic and technology characteristic, which influence the utilization and task performance. This is the conceptual model of integration of UTATE and TTF model. We integrate, as you see, TTF with the UTATE model in order to have or to provide more powerful model which have much ability to help to discover and identify the factors. This integration model seems to be the most relevant conceptual framework for this study after reviewing other technology acceptance theory. Each model has different advantages. UTATE focus on the study of the behavior of the user and pay a little attention to the degree of the fit of the technology for the task. The integration between models will help to discover more factors which support successful adoption of CDSs. We use a qualitative research method to collect data by conducting semi-structured interview. 54 interviews have been conducting with a general practitioner in 3 stages to obtain their perspective and attitude regarding the factor that influence the acceptance of CDSs. In the first stage, I interviewed with the 12 general practitioners through using a convergent interviewing approach in order to generate more factors. In the second stage, I interviewed with the 42 general practitioners to discover and identify the factors of the models. This stage helped to understand more about the factors that influence of the acceptance of CDSs through collecting their respective beliefs, attitudes regarding CDSs. In the third stage, I interviewed with just 3 general practitioners from the stage number 1, just to review and increase the validation of regarding the final model. We use thematic analysis to analyze the data. Thematic analysis is a technique for classifying, analyzing, summarizing themes from the available data. Thematic analysis is help us to provide a flexible approach to identify themes. Thematic analysis is a useful method for summarizing large sets of data. This is the final framework of the study. The study results show that the following factors influence the acceptance of CDSs by general practitioners, which are performance expectancy, which include the time alert, accurate, reduce errors, treatment plan, and other factors as well are effort expectancy and facilitating conditions, which influence effort expectancy and facilitated condition, including training, technical support, updating the system. Also, the task technology fit, technology characteristic, and task characteristic, and accessibility. And also another factors are patient satisfaction and connection with other doctors, and perceived risk, which are include the time risk and functional performance risk of the system. Most of the general practitioners in this study indicate that the influence of UTAT and TTF models factors, except the social influence factor. Healthcare in developing countries need more improve in healthcare system in order to better understanding the health protocols, and also to reduce the medical errors, to provide better healthcare services. This framework developed in this study provide a new approach that's helped to understand the factors that influence the use CDSS. This model will help a lot the researchers and developers of a medical system to design more successful system. This is the references. Thank you so much.
Thank you very much for your presentation. I'll ask our two chairs in the session, Dr. Dioma and Dr. Rathod, if you have any questions.
I would like to ask about did you consider the hardware requirements for this implementation, and also the computational complexity for this solution implementation further?
Yeah, actually, in this study, I focus on the just qualitative research method, using semi-structural interview just to investigate and research and discover more factors that influence the acceptance of CDSS. This is the main aim of this study, to research and discover about these factors, which are a lot of studies indicate that there is limited study showing the factors that influence the acceptance of CDSS in developing countries.
Thank you.
Thank you very much for your presentation, sir. We'll move on to our next presenter, who is Alyssa Kwanpinon from Thailand, and her paper title is COVID-19 X-ray image diagnosis using deep convolutional neural networks. Welcoming you, Alyssa. How are you doing today? If you want to unmute yourself, and we can start with your presentation.
Okay, thank you very much. Okay, can you see my screen?
Yes, we can see your screen and hear you as well.
Okay, my presentation, my name is Alyssa Kunapinan from Asian Institute of Technology, AT, in Thailand. My professor is in Dr. Matthew and Professor Matthew Daile. This is one of the machine learning project in the coursework. Okay, my presentation is a COVID X-ray image diagnostic using deep convolution neural network, or deep CNN. That is maybe everybody know about that already. So in my content, there is okay. My content has an introduction. Deep learning COVID is mean our name of the deep learning CNN for use in X-ray detection, and experimental design, result, and conclusion. Okay, from that, everybody know the COVID-19 is make everybody stuck and must stay in home, and because it's cause effect to every the person who infect that is have around 3% die. So so many people try to detect the infected person, but it's very difficult because they need to use the swab inside the nose, and then need to at least 1 or 2 hours, or as in Thailand at least 6 hours. So many people don't know that we are infected or not. In China, some case they use CT scan for predict the X-ray, predict the infection of the COVID-19. But is for me, for development country, CT scan is a 3D X-ray that is have a lot of cost for many patients. So in my thinking, I think I should use, we can use the X-ray image for detect the COVID-19, because it's the cost is lower than CT scans a lot. Also, the timing for detect that is very short. So in my project, I want to classify between COVID-19 to auto pneumonia and the normal by using CNN. My main project, I use LessNet 18 and Inception LessNet v2. So in X-ray image, when detect in COVID-19 or pneumonia, it has some smoke light feature that can indicate disease. But for I asked many doctors in Thailand, they said some a little bit evidence that can detect COVID-19 in X-ray image, but they cannot confirm that the X-ray image can classify between COVID-19 or pneumonia. So I have research from China that they say CT scan can classify because the characteristic of the smoke light in CT scan is different from the X-ray image. So we hypothesize that it's possible that X-ray image can classify COVID-19. So we use deep convolution neural network because deep CNN have already used in analyzing X-ray image in other applications. Okay. Why I select LessNet 18 and Inception LessNet v2? LessNet 18 is one of the most popular classification model that is very good performance in ImageNet dataset, and is faster to train, that it can confirm that we can know very fast that our thinking is correct or not. And another one model is Inception LessNet v2, because we believe that the larger or deeper network structure may more suitable than the simple model. So I prepare the data from Kaggle around 3,000 X-ray images. in there have the 3 cars, 1,500 of normal image, 196 of COVID-19 X-ray image, and 1,463 of pneumonia image. And in from the 3,300 X-ray image, I separate to be 80% training, 10% validation, and 10% test. So after I try to train the ResNet 18 while training it from scratch, I found that the overall accuracy of the classify between normal COVID and pneumonia is 95%, and I can classify. 91% is it should be more correct. 91%, and for detect COVID-19, it for correctly is 86%. Then I try to classify ResNet 18 with transfer learning. Overall of the classification correctly is 88%, and COVID-19 is 91%. So I changed to classify inception ResNet V2 by train from scratch. I found that correctly is 92%, and it can detect COVID-19 is up to 96%. Then we believe that if we add more additional inception ResNet models, more deeper, we should have the result is better. So the result of overall is 93%, and classifying COVID-19 is at 96%. So I try to separate between normal and not all pneumonia about X-ray image. If we use inception ResNet V2 with the modified expand network is up to 93%, and if we try to separate COVID-19 with author of pneumonia, is up to 93.5%. So it's better than author normal network. So we think about why COVID-19 and author pneumonia is neural network can be classified. So I try to use the gradient distinguish by with this algorithm. So I try to use some pneumonia image and try to check that if we try to detect as the COVID-19, what will be happen. So the result of it here. So the red color, and we should interest about red color and blue color both. That is try to say somewhere. I will explain only inception ResNet with modified model in the photo 2 because it's more clearly. It's look like it show that has some big difference in branch of bronchia of in the lung. Okay. For conclusion, we can summarize that deep learning can classify COVID-19 lung by using X-ray image. But however, the data available of COVID-19 is very little now. So if we want to continue the project, we need to have more COVID-19 X-ray image. And if we improve CNN network, it should be more efficiency. Then after it's accurate enough, we should make the online service for X-ray image to enable everybody in for every hospital in Thailand can use the software. So the cost about detection COVID-19 for infected person will be lower than currently. Okay, thank you.
Thank you very much for your presentation. Do either of the chairs have any questions?
I have a question. Your presentation was very nice, and I think your topic is also very nice because it's useful for the society also. Like you are going to use X-ray images to identify whether the COVID-19 infection is there or not. So can you tell me? You told that you collected around 3,000 X-ray images. So what was the source of your data for collecting those 3,000 X-ray images?
Source code data. You mean the programming code?
Yeah. How did you collect those 3,000 X-ray images? Like
I collect from Kaggle. There are a lot of X-ray image in Kaggle from I think I think from Wuhan has been published in for free source code.
Those X-ray images was from Thailand or some other country?
From many countries.
Many countries. And you also told that like for training the data set, you must have taken some parameters. So what was the parameters you took for that training the data set?
The parameter?
Yeah. For the training.
Parameter for training?
Yes.
I just use the lung X-ray image only, and then say this lung is a normal, this lung is a pneumonia, and this lung is a COVID-19.
But how do you identify whether it is a pneumonia or non-pneumonia?
The data set in Kaggle already set it in as the label already.
Okay, fine. Very nice. Your research is very nice. It's useful for the society.
Thank you very much.
So congratulations.
Thank you very much for your presentation. Moving on to our next presenter, Ahmed Musa. If you're here, sir, if you'd like to, there we are. I'll ask you to unmute yourself.
Yep.
That's perfect. I can hear you now, sir. Yeah. I'll stop sharing my screen and allow you to share your presentation.
All right. Can you see my screen and can you hear me?
It's just loaded. Yes, that's it. We can. There are some gray bars on my screen for certain reason.
We can see your screen. We can see your screen. Yes, it's visible.
Okay. Is there any overlay or something?
Nothing. Nice.
Okay.
Yeah, it's okay.
We can go ahead.
All right. So my name is Ahmed Musa, and the topic of my research is the extraction and generation of color palettes with adversarial variational autoencoders. And it's not related to health or bioinformatics or anything like that. But if you want to think about the problem in a different way, you can think of it as an image to sequence translation problem. So a little bit of background about the topic. It's that color palettes, they're quite an important part of everyone that works in design or illustration, and they use it generally on a daily basis. However, it's usually difficult to explain why certain colors look good together, or why a color palette is aesthetically pleasing. And when something is usually difficult to explain, it's even more difficult to formalize it into an algorithm or algorithmic rules. Usually for a person that is not experienced in this field, it will take them a very long time, or maybe they're not even capable of creating a nice looking color palette. And it's probably even harder for them to extract it from a digital medium like an image. And another motivation is that there's a lot of web services that provide a tool where you can, for example, drag and drop an image, and it will automatically extract a color palette from that image for you. But usually it's not transparent what kind of algorithm they're using, which takes us to the related work section. Traditionally, the main methods to create a color palette from an image are based on clustering and quantization techniques, and like k-means and other clustering methods. And arguably one of the most popular ones is currently the modified median cut algorithm. And as you can see from the image, their objective is not to create a pretty color palette. It's mainly the quantization of the image. Newer approaches, they use deep learning methods, like models like Pix2Pix, if you're familiar with them. So what my objective is to create a system that can generate new color palettes and is capable also of extracting them from an input image. Another constraint is that this system should be able of generating a variety of different palettes for a given image. So at its core, my proposed model is based on a variational autoencoder. As opposed to the traditional autoencoder, the variational autoencoder has generative capabilities, meaning that it is capable of generating new data samples. The way this is done is that in addition to training it with a reconstruction loss, you also train it with a regularization term, which in this case is the callback library divergence. This regularization term ensures that the latent space, that the learned latent space is regularized, which means that any given latent code, if you decode it with a decoder, it will result in a meaningful data sample, which is not true for the traditional autoencoder. So the variation autoencoder has seen a lot of success in many different fields, like image processing, or also bioinformatics for single cell RNA sequencing, sequence analysis, for example. So what is our proposed model? It mainly consists of three components: a convolutional neural network to encode the image into a latent space, the sampling layer that usually variational autoencoders utilize, which allows us to sample latent codes, and implements the reparameterization trick so that the gradient can go back to the CNN. And the decoder, after a lot of experimenting, found out that what works best is using an RNN to generate the sequence of colors, which is essentially a sequence of tuples of RGB values, if you want to think about it like that. So essentially, the problem consists of converting a grid of pixels, that is the image, to a sequence of pixels that have some correlation between them. So that's the main proposed model. After experimenting more, I came up with this second model that borrows an idea from the generative adversarial networks. And in addition to the, basically we replace the reconstruction loss with a learned similarity metric. This learned similarity metric, you can do it by utilizing discriminators. So in this case, you take the output from the RNN decoder, which generates the palette, and you pass it on to the discriminator which will be trained to discriminate between fake and real color palettes. And it will send back a gradient to the RNN decoder to train it. And in this case, we use two different types of discriminators. One that is trained to differentiate between real and fake color palettes, and a secondary discriminator that is trained to differentiate between real and fake color palettes, but we also pass to it the input image. This is to ensure that it learns the correlation between the color palette and the image. Additionally, to the latent vector that is passed to the decoder, we also pass an auxiliary noise vector, which you'll see what the purpose of is in the coming part of the presentation. So that's the second proposed architecture. The dataset, for the dataset to make a useful dataset, we need pairs of images and their corresponding color palettes. And personally, I don't have the skill to make such a dataset. So we scrape two websites, namely Design Seeds and Color Palettes. We ask the hosts of the websites if it's okay to scrape them, and they gave us the confirmation. So after the scraping, we end up with around 7,000 color palettes and their corresponding images. And you can see that the Design Seeds website, the color palette consists of 6 different colors, whereas the Color Palettes website has color palettes with 5 colors. So what we do as kind of a data augmentation is for the color palettes that contain 6 colors, we drop randomly one of the colors from the palette. And we end up with around 7,000 images and palette pairs. For pre-processing, the only thing that we do is that we, instead of using the RGB color space, we use the CIE lab color space, which has been shown to have a little bit of advantage over the RGB color space for deep learning methods. Okay, so for the experimental results, first, our first model, the CNN VAE RNN, you can see that so basically what we do is we generate 2 random latent vectors that we sample from a Gaussian distribution, and we decode them with the decoder. And we also compute the interpolation between those 2 vectors and decode them with the decoder. And you can see that there's a smooth transition between the latent vectors. And at the bottom, you can see the color palettes generated for the images. However, you can see that it makes an attempt at generating a palette, but it's not very fitting towards the image. So for the results of the VAE GAN, you can see that the color palettes are much more colorful, and you get a variety of color palettes, which is due to the auxiliary noise vector that we also fed to the decoder in addition to the latent code, which we got from encoding the image with the encoder. So we leverage basically the problem of having palettes that don't really fit. We leverage it by giving a choice to the user to select a palette that they would maybe like. And in this manner, since we have 2 kind of latent vectors, we can fix one and interpolate the others. And in this manner, we can get sort of a grid of different color palettes for by interpolating them one at a time. And here you can see some examples. Okay, we also do a kind of evaluation where we measure 2 scores, fittingness and prettiness. First, we ask the person that we tested to evaluate the color palette that was created by a human from the test set. And you can see that even the human palette does not get a perfect score for prettiness and fittingness. And the VAE model, it gets around, it's close to the human score, but in fittingness, it doesn't perform very well. The VAE GAN does not perform very well in fittingness, but a little bit better in prettiness. But this is just kind of a primary evaluation. The model obviously still needs a lot of improvement for the accuracy of the colors. And but one nice thing about the model is that depending on the data set, we can actually capture very specific aspects of the human color selection process, since the color palettes in the data set are all created by actual human designers and persons that deal with colors. Other algorithms probably aren't capable of doing that. So future work would probably involve creating a much larger data set and seeing how the model would perform on that and further improvements to the model. So thanks for listening. If you want to contact me later, here's my email, and the code is on GitHub if you're interested. So thank you for listening.
Thank you very much for your presentation, sir. If you had any questions, sir.
I have one question. As you told in your comparison, like prettiness and prettiness. So prettiness is results are very nice, but why the results are very not good in this prettiness? Have you analyzed that?
Why does it not perform very well?
Prettiness is not giving the good results in your model. So what can be the reason? What can be the reason in your opinion?
And my opinion is that it's not enough data. Like for generative adversarial networks, you need some, like usually tens of thousands of data samples, and we only have
the same amount of data you are using for the prettiness also.
Yes, it's the same model.
But for prettiness, you need less amount of data. You want to say that?
No, the more data, the better for both.
But prettiness is giving, I think, not very good results.
Yeah.
So we need to work on that. Huh?
Yeah. I think the main reason is that people are very picky. Like if they see, if it doesn't fit exactly to the image, then they give it a low score. Yeah.
Okay, fine, good. Work is nice.
I would like also to ask one question, maybe two. What was the size of training and validation set, and how long does it take to obtain a final palette for a single standard image?
Okay, so the training, we did a 80-20 training test split. And a forward pass is instantaneous, basically. You just feed the image to the model and it immediately gives you a palette in some milliseconds. So that's also an advantage in comparison to like clustering methods.
Thank you. Very good work. Thank you.
Thank you.
Thank you very much for your presentation. I do not believe that our next presenter, Patrick Morder, is present. Is anyone here from his team, any of his co-authors that are here to present on his behalf?
I think no one.
No, we'll move on then. I think also the same case for our next host, Ricardo Vadasca. I don't believe he is here, or is there anyone else here to present on his behalf? So on a chat, someone says something. Benedict Schnell, who are you meant to be presenting on behalf of, sir?
Same. No one here. Behalf of him.
Let me ask you to
Yes,
unmute.
hello. Can you hear me now?
I can hear you now, sir.
Yeah, sorry. Can you go one slide back, please? I want to say the apologize from Patrick that he cannot give the talk today, but I would be happy to give the talk.
Not to worry. Thank you very much, sir. I'll allow you to share your presentation.
Thank you. Okay, you should be able to see it now.
Yeah, we can see and hear you.
Okay. So good afternoon to all the listeners, and thanks to the hosts and the organizers from ICICT for the invitation. I will give a review about the latest developments in smart health concerning the challenges in smart health applications using the wearable medical Internet of Things. So we, myself, Benedict Schnell, Patrick Morder, Hans Ehm, Marcel Konstantinov, and Mahmoud Ismail at Infineon, we conducted a review last year, which we're happy to present now. So first of all, for some wording to clarify some definitions, we have the smart health in the Internet of Things. And basically, there's been a development in the last couple of years or decades where the e-health has developed into smart health. And concerning the e-health, which was like some computers to keep track of medical records and share them from place to place, it has developed into m-health, such as to capture or access medical information on mobile devices, and hence the term M in the m-health. And it has been recently developed into smart health, where devices are having actually built-in intelligence, and that also refers to other terms in the Internet of Things, such as smart city or smart home. And for a motivation here, we were looking at what actually the driver of that technology is. So is smart health itself as an emerging application in the overall IoT domain, or is it more driving some of the technology? And here we can see that some of the basic architecture of any kind of smart health or medical Internet of Things architecture, which will consist of several layers, and you will eventually have such as the edge layer on the left side, and you will have some of the other layers such as fog layer and cloud layer, and eventually the application layer where the services of the health industry lie. So where we have on the edge layers different types of devices to have vital sign monitoring or health tracking of basic fitness applications, and we will have to use that and use the signals to be transferred to the cloud layer where the server relies, and eventually have some application layer where other things like the remote diagnostic relies, and also early warnings are triggered also for emergency cases. And if we go on and we analyze now that particular link between the users and their smart wristbands or smartwatches, whatever it might be, and the application layer, we see that we have on the one side some systems, might be hardware-based or software-based, and the services of the health industry. And here we can see that we have some systems which consist of other more subsystems, and also one system that fulfills at least one service, but also those health services which consist of several microservices or sub-services, and that service is also being fulfilled by various systems, at least one system. And now we have an increasing advancements in technology going on in that systems, and also an increasing amount of medical services in the MIoT, on the medical Internet of Things. And how are they interlinked with each other was the question here. And we see that also in smart health context. I bring out this quote that it's the provisioning of health-related services using a network of context-aware intelligent agents. And with agents, we can now refer here to systems or even hardware-based systems. So we conducted a literature research. We used the IEEE Explorer here, and we fitted it with some keywords, combined it with Boolean logic from the last years, from 2015 to mid 2020, where this research was conducted. Later did some classification of those publications for some tendency and for some further narrowing. And finally did some comparison of those publications where we saw some similarities in the findings, and also derived some common challenges and new solutions. So I want to dig into the IEEE Explorer search we conducted here. First of all, we had a couple of keywords we derived from several publications from the last years, and we fitted them into these bins where they have been grouped up in order to combine them with OR operators, and finally with an AND operator, and fitted it into the search engine. That helped us actually to find publications that had at least one of those keywords in that bin, and we finally came up with 48 publications. And for some further classification, we looked at the statistics that those publications were focusing on. First of all, we saw that there was a basic upwards trend of the overall number of publications per year. And secondly, that besides we were explicitly searching for edge computing, we also found that the edge computing environment was having the biggest amount of increase in publications over the last years. Further, we saw that based on the solutions offered in the publication themselves, Some of them focus on systems, some of them focus only on the medical services that were offered by the technology. We saw that there was an enduring attention on the service approaches, but the strongest focus was on the system side here. And we also found that some of the publications actually focused on the smart health application only, and some of them focused on other IoT domains such as the smart health, smart city or smart home environment that I already mentioned. So we did some selection criteria here, and first of all is that, was I already mentioning, that the edge computing environment was the area with the highest demand for us, because we saw that the strongest growth here, and also that the smart health applications were the highest interest for us, of course, since this research was conducted in this field. And third, that we consider the service and the system approaches equally, since they have been distributed equally over the last years, and so we kept everything on that side. And we had an amount of 17 publications remaining. And to further put them into perspective, then I want to highlight them with the common problem areas that were addressed with these publications. So first of all, for our first result, I want to highlight again the overall structure on the different computing layers we have in our IoT application. And we saw, first of all, that some of them were focusing on latency, especially between the edge layer and the fog layer, such as the Wi-Fi and Bluetooth connections here, and also 4G and the latest technology in 5G connection. Secondly, we found some publications focusing on the security, on the technology, on the hardware device themselves. Third, we had publications focusing on the service availability by the medical sector. And also we found some focusing on data offloading and also the data processing and the intermediate fog layers. And also some publications focusing on the connectivity in general and the overall architecture of that whole system. And also some big data analysis focusing only on the cloud applications and all the algorithms relying on that layer. And if we look at that statistics again, we see that we have some more like even out, and the publications were spread throughout all of these problem areas. What's most interesting here is that most of the publications focusing on that broad fields and focusing on problems reaching from the edge layer to the application layer itself and all the connections in between. For our second result, we looked at the implementations which have been done by most of the EU publications. So when I say implementations, we mean that most of them actually implemented some prototypes, either software or hardware based, in order to conduct their research and their innovations, to test modern innovations. And they were mostly focusing on either power saving or data security. And the remaining publications were not focusing on either of those both. So we did not make any more effort to put them into final grouping here. So I want to highlight the progress which was already done by most of the publications here. And most of the progress was most of the projects were only partially completed, and most of the publications only addressed sort of as an intermediate step of their overall research. And we can derive a point here which we say that the publications only address some of their research, and also that this research field is really ongoing and many research has still to be done, and it's also in most of the objectives of those researchers. So that gives us some room for discussion, and we saw that in terms of the power saving, of course, one of the boundaries here is the physical hardware boundaries in general. And we have some limited energy efficiency since we're dealing with battery run devices, and that energy consumption of those devices is almost very highly linked to the workload itself of the device, such as wearable computing or your smartwatch, which can do several algorithms, but on the cost of or the expense of a higher battery consumption. And a solution option here, we derived that the resource allocation and the data offloading is really important, and so that the data can also be offloaded to other layers, or even to intermediate layers such as your smartphone or other gateways in between the cloud and the edge device. And we kind of derived that here the processing as a service might be an upcoming trend here. For the data security, we saw that the overall solutions offered were kind of fragmented, and many of the publications focusing on their very own solutions, and there were no intermediate solutions offered between those research. And we derived that as a lack of standards for, let's say, the secure computing, and the computing paradigms are also fluid, let's say, from cloud computing to edge computing to fog computing. There might be different solutions offered, and every solution includes a different kind of security mechanisms. And here a solution we derived might be that it might be helpful to stress the service itself during the design process of the whole architecture. So service would mean the overall health service or the service as a secure computing. To stress that in the whole design process might be beneficial here. For the general publications here, we don't have any more decisions possible, but I want to use that room to highlight our limitation of that research. Of course, we only analyzed a fraction of the whole IoT domain in general, and we also analyzed only the publications which were released via the IEEE. And whilst we were having only a really fragmented amount of research here, the smart health in general was kept too broad, and in our opinion, since there was not because it would be helpful to use any kind of wording that is more specific in terms of the overall application. Let's say it could be smart monitoring or remote monitoring or remote health diagnostics, which would have been to give more profound results. So as a conclusion, I would say that we had our findings, which was that the edge computing is getting more and more attention, and the computing itself of medical Internet of Things is moving towards the edge devices, such as wearable computing and sensor networks. And also there's a lack of system standardization, and that is due to the rapid evolution of technology, which makes some old standards obsolete and also gives new room for new standardization. And the challenges which were highlighted here was the energy efficiency of the processing. That gives them sort of like a trade-off between the battery consumption, the data and the transmission accuracy, and also the size of the devices themselves. And also the cybersecurity is really important here, since we're not dealing with any data, but with highly confidential medical data. And that is of really high concern in the smart health context. So that will be all from my side. Thank you. And if you have any questions, please let me know.
Thank you very much, Benedict, for your presentation and stepping in on behalf of Patrick. Do either of you chairs have any questions?
I would like to ask, because in this context, very important is also communication layer. I didn't see any keywords related to communication layer, also robotic algorithm, wireless, wired communication with the sensors. Could you comment this?
I would say that the communication layer itself, it's always a question about the perspective, since we only focused here on the system and also on the service side of the medical services. I would say that the communication layer acts as a layer in between those computing layers that are highlighted. So between edge and cloud, you have, of course, a layer which connects those two layers with each other. And that would act as another communication layer, certainly. But here I wanted to highlight the computing layers, which are the edge layer, the fog layer, and the cloud layer.
Thank you. Thank you.
Thank you very much. We'll move on to our next presenter, who is Mr. Ricardo Verdasca from Portugal, whose paper title is Towards an Effective Decision Support System for Diabetic Foot Ulcers, Diagnosis and Treatment Assessment. Welcome, Mr. Verdascas. How are you doing? And I hope you can hear us.
Yes, I can. Thank you.
Perfect. If you want to now share your presentation, feel free and to get started in your own time. So thank you.
just a bit. I think you can see it.
Yes, we can see that perfectly, sir.
Thank you. Just looking at us. Hello, everybody. My name is Ricardo Badasca. I'm a computer science professor at Isla Santarém in Portugal, and I'm here today to present you my research on the topic towards an effective decision support system for diabetic foot ulcers, diagnostic and treatment assessment. First of all, I would like to describe you the contents of this talk. That will be introducing the motivation with the disease of diabetic mellitus and the diabetic foot disease. Then I'll provide you an outlook on the existing data sets and also on the existing decision support system solutions, which is the current diagnostic criteria for diabetic foot disease, which are the emerging diagnostic methods, and a proposed solution for solving this problem. And I will close with some remarks in the end. Diabetic mellitus is a metabolic disease which affects a large range of the population and is the most growing health threat to humans. It affects at the moment 1 in 11 persons in the whole world, and there are regions of the world that are more affected than others, with special here in the Mediterranean and eastern part of Europe, which is increasing a little bit more than the rest of the world. But it provides a lot of complications that can go from blindness, some kidney failure, some cardiovascular associated problems, but also some problems that affect the extremities and in particular the foot, which can lead to amputations. That is caused by two sources, which can be a deficit in the peripheral blood flow, but also in the neurosensor system. So we can have three types of diabetic foot ulcers. That is a wound that can be generated because of poor blood irrigation. And the three types are neuropathic, neuroischemic, or ischemic, depending on the affected systems. It starts with no open lesion, but with the temperature increase close to the skin, and then a superficial ulcer can generate a deeper ulcer, an abscess, and it can end as a gangrene situation that can lead to an amputation. It can also lead to deformations on the foot. Just for you to have an idea, about 19 to 34% of people with diabetes will suffer with the diabetic foot ulcers in their lifetime. And 1/3 of these people affected with diabetic foot ulcers will have an amputation. And also statistics show that 75% of the people that have an amputation, within 5 years, they will die. So this is a very serious situation and is growing exponential. In terms of treatment, I'm presenting you this chart here. You have here a representation of the normal wound healing with all the structures underneath the skin, also regenerating very well. But in the case of a person with diabetes, it is not the same. And in terms of treatment, what normally we have, we'll have regular sharp debridement, offloading, and advanced wound dressing with new products coming out, and also antibiotics when you have a presence of an inflammation. And again, 1 in 4 people with diabetes are affected with diabetic foot ulcers. This is very serious. So the problem here is to provide a critical overview of the existing decision support systems and publicly available research data sets for diabetic foot ulcers, early diagnosis, and treatment assessment, and propose a new infrastructure system to deal with this, overcoming the past attempts. When searching for the existing data sets in Kaggle and other sources, we only could find 10 openly available data sets that could be used for diabetic foot ulcer. None of them were exclusively for this application. The sample size of that available data sets would range from 200 to 45,000. Most were generic diabetic mellitus characterization data, and that normally we have glucose values that were assessed daily, or even presence of blood pressure, or if the person takes tobacco or something like that. And one that was very interesting was with 11,830 samples and was with genetic data, but mainly the genomes that are responsible for the diabetes disease itself. In terms of decision support systems, we have found 18 and the literature reported, but only one was dealt with the risk identification using only 255 samples and achieved an accuracy of 83% using artificial neural networks. It's actually a very good value for accuracy for these systems. In terms of diabetic foot ulcer prediction, we found one that using logistic regression with Bayesian networks operating in 234 samples, using 80% as training, 20 as test, and achieved a 76.5 accuracy. In terms of classification, the maximum accuracy was found in 99.1% in infrared thermal imaging using a cluster k-means with only 76 samples. The largest database was found of being composed of 53,354 samples and achieved 84.2 using the gradient boost tree on classifying wound towards healing or non-healing. So, just for you have an idea, the current diagnostic criteria uses some sensitive tests like Doppler for assessing the blood flow and also the measurement of O2 on the blood, on the extremity, but also the tuning fork or the monofilament that is using to touching one of these points and asking if the patient has any sensation or not. This is very dependent on the perception of the patient, are not very objective, but is what is used nowadays. And they normally grade the risk of a person in danger of having a diabetic foot ulcers in very low, low, medium, and high risk. This is, along with this, they also use the classification criteria of the International Work Group of Diabetic Foot, and also the Wi-Fi system that grades also the risk of having a wound, and if the wound is already present, it can be also assessed using the Wagner scale or the University of Texas wound classification scale. Although research has been going on in this area and some new emerging diagnostic methods have been tested and assessed. One is, for example, gait analysis, the way the person walks, and also it shows a pattern that is typical of a person that is in high risk of developing a foot ulcers, because they will not have the same gait of a person that has no problems. Also, in terms of plantar pressure, we can look at here, for example, is an image of a pressure of a person that has normal pressure on the feet, and here on the right side you have a person that have diabetic foot problems already. Also, the infrared thermal images, and this is one image I took a few years ago of a patient that has an active ulcer. Actually, he has ulcers in both feet. Here he has a neuropathic, and here he has a ischemic. And these records the infrared thermal imaging, the surface temperature of the skin. And normally, with an infected wound, is associated with rising temperature, inflammation. These images can be analyzed using, for example, the most common locations of the diabetic foot ulcers, or using the angiosomes, which are vascular areas that irrigate parts of the feet. Also, another interesting research that is being done is looking at the biomarkers that indicate the probability of development of this problem or not. And when the wound is already visible, also they are using now the pressure ulcer scale for healing, which is a much more objective scale than the previous ones, the Wagner and Texas. Given this, and since we have seen the existing decision support systems, the existing data set, that the data that is present in that data sets and is being used by that decision support system is a little bit apart from the reality that we see in the clinical side, we came up with this solution. In terms of building our data warehouse, we need data from multiple sources, like, for example, the patient history database, diabetic foot ulcer regular consult, where they will have assessed with international work group criteria, and also with the Wi-Fi. Then the daily diabetic needs monitoring, where they have, for example, the blood pressure, the glucose level, and then the treatment assessment with the scales, the objective scales, like I just showed you the push scale when you have the ulcer, or the promising exams, like, for example, looking at temperature. And in terms of skin temperature, if you have, for example, an asymmetry between left and right areas of the foot with more than 2.2 degrees, that is a high sign of being in danger of developing an ulcer before it is visible. And also a database of biomarkers. And if you combine all of them and you apply the extraction, transform, and load to populate your data warehouse, having one of these data sources in the data mart, you start having multidimensional data. And along with that, if you build a multidimensional data in the online and analysis processing cube, you can look at it from different perspectives. And if you use, for example, a star schema centered on the patient, you can have a perspective in each one of that data sources and combine them, building, for example, a smart dashboard where you could have a result of each one of that current used exams or promising exams that can allow you to do a much better decision. In order to conclude my remarks, I will, because it's getting close to the end, there is an absence of freely available large data sets with all the information needed to do an accurate decision. It also seems that informatics and computing researchers and developers have been distanced from the current diagnosis and treatment procedures used by the clinicians. So it seems that there is a lack of communication between both. And the decision support system based on OLAP Cube with the star schema would completely facilitate multidimensional views and help to generate more efficient dashboards that would help clinicians to do a much better decision. And I would like also to say that the existence of diabetic foot specialists is very scarce in the world and is not available in all the geographical locations. So a solution like this is really needed because we are facing a worldwide problem that is growing a lot. And thank you for everything. This is the location of Santarém, and you over here, nice views from the city. And I'm open to questions.
Thank you very much for your amazing presentation. Do any of the chair members have a question?
I would like to ask you if you considered in your proposal solution implementing some layers according to NoSQL databases.
Yes, actually, the way I show with that architecture based in data marts can use either relational databases or NoSQL databases.
Thank you. Thank you very much.
Thank you very much.
I don't have any question, but I want to appreciate your work. it seems very nice work, and yes, such a good contribution. Thank you
you
so
very
much
much.
for presenting such a nice paper.
Thank you.
Thank you very much, Mr. Ricardo Verdasca. We'll move on now to our next presenter, Janina Suhr from Germany, whose paper title is Increasing the Quantity of Treatment with Medical Apps Through Remote Compliance Testing. Welcome.
Hi.
Hello. What I'll do now is just stop sharing my screen to allow you to get your presentation up and running, and you can carry on in your own time. We can see that now and hear you also.
Gorgeous. Then I start. So thank you very much. Hello, I'm Janina Sauer from the Karl von Ossietzky University of Oldenburg in Germany and the University of Applied Sciences Kaiserslautern also in Germany. And I'm going to talk about my current work, how to increase the quality of the treatment of medical apps with the help of remote testing. Smartphone application in the medical context, so-called medical apps, are becoming more and more important. They enable health professionals and patients to stay in closer contact regardless of their location. Furthermore, medical apps inform the patient and give him or her a comprehensive picture of the illness or the treatment, thus increasing this patient's self-administration. This alone may already have an effect on compliance. An accurate assessment of compliance behavior is necessary for effectiveness and an efficient treatment planning to ensure that changes in health outcomes can be traced back to the recommended gene. An ideal measurement approach would be unnoticed observation, which is difficult to implement under real-life conditions. One of the measurement approaches is to simply survey medical staff and patients about their subjective assessment of compliance behavior. But this survey is prone to errors in many respects. Objective strategies also lead to drawbacks in assessing compliance. Each disease and treatment has its own compliance challenges and thus its own nature and complexity of measurability. For most apps, it's advisable to use individual events, timestamps, and counters. These events are often buttons that are used to initiate or terminate functions in the app, for example, to save a data entry. Timers and counters can be very easily integrated into existing program code with a little additional effort. By remote testing, the mobile application can be evaluated in everyday situation without the test subjects having to come to a usability lab. All functions are naturally tested in their usability in real-life situations. This method can be adapted to measure compliance. Thus, it shows when the patient uses the app, when which entries are made, and how often. It can be compared whether these times, periods, and numbers correspond to expectations. If necessary, it's possible to influence the use and thus the treatment by directly contacting the user. In order to be able to track patients' activity even more precisely, the time required to make an input can also be checked by timestamping each start and end point of an action. In this way, the duration of an input can be checked and compared with the target values. The data already entered is subjected to a plausibility check, which in this case means that the values are within a usual range. After a longer period of use in line with expectations, the input should show a success. This depends on the reason to use the app in the first place. The remote compliance measurement method is useful for testing the app before it's released on the market. In this way, it can be tested and evaluated in everyday situation, and if necessary, the app can be optimized. On the other hand, the compliance can be checked permanently even after the app has been launched. This way, the supervising health professional has an overview at all times whether the patient is using the app as expected and can intervene or adjust the treatment if necessary. From the point of view of long-term compliance, possible learning curves and habits can be identified, after which the treatment and associated use can also be adjusted. However, the quality of experience must be considered in any case. A disadvantage of a remote testing is the local separation of the test leader and the test subject. When using a smartphone, observation can be the front camera to interpret facial expression makes little sense, and the data protection is complex. A way must therefore be found to ensure that the data quality is adequate. By measuring patients' activity, statements can be made about the data quality. If the entries are made faster than usual compared to the previously defined standard value of the individual patient, this suggests a hectic, stressful situation which leads to errors. Biofactors are another point of measurement for data quality. Common biofeedback point for stress is pulse. The increase in pulse in stressful situation can be measured via the built-in smartphone camera. If the pulse is elevated from the beginning, the entry is made in stress.